All right. Exam 4, essay question 3. So, let's go ahead and read the question. Explain all of the membranes, pressures, and mechanisms that make negative pressure ventilation possible. Describe what a pneumothorax is and how it occurs. What is surfactant? What does a lack of surfactant impair? How does a lack of surfactant impair ventilation? Explain how CO2 is transported in the blood. Describe O2 transport in the blood as well. Include a description of the oxygen hemoglobin dissociation curve and factors that influence the affinity of hemoglobin for oxygen. Sorry. How do these factors affect the oxygen hemoglobin dissociation curve? Okay, so let's get into our membranes and pressures and mechanisms. So let's go over the membranes first. Inside of our lungs, the parietal pleura will line our thoracic cavity. Our visceral pleura covers the lungs and our intrapleural space. This is technically a membrane that I wanted to include. It's a thin fluid-filled space between these two membranes, so it's there and it just has the fluid in between them, separating them, filled with that fluid. All right, our pressures involved is going to be our atmospheric pressure, and this is the pressure of the air outside the body, our intrapulmonary pressure, and this is the pressure within the lung alveoli, and our intrapleural pressure. And the pressure, this is the pressure inside of the pleural cavity, and this is typically negative relative to both atmospheric and intrapulmonary pressures. All right, mechanics of breathing. So there's first inspiration, taking in a breath, and this is when the diaphragm contracts and it moves downward, and our intercostal muscles will expand the chest cavity, and that will decrease our intrapleural pressure as our volume increases of our space where our lungs are located. This negative pressure pulls the lungs outward, so we're pulling our lungs with our chest, and this is going to lower our intrapulmonary pressure, and that's going to allow it to flow in, because we're just creating such a vacuum of volume increase that it pulls air in. Much like taking a syringe and putting your finger over top of the syringe and then pulling down the plunger, that's increasing the volume, and so air naturally wants to go into it. And so once you uncover it, that air just goes straight into the syringe. The next mechanic is expiration, breathing out. This is when our diaphragm relaxes, meaning it comes back up, and the elastic recoil of our lungs and chest wall are going to increase our intrapulmonary pressure, and that is going to push the air out. So, pressures, mechanics, and membranes. All right, let's move on to the pneumothorax. So this is a pneumothorax is when there's air inside of our pleural space, and this is going to disrupt the negative pressure balance. So what could cause that? This is an injury, trauma, a puncture wound, spontaneous rupture of lung tissue can also happen as well, or medical procedures, just pop a lung. So take back our syringe model. If there's a hole in the bottom of the syringe and I'm covering it, when I pull that syringe, the air is just going to flow into the hole. There is a better mechanism or a better model to use this, and that's a marshmallow inside of the syringe. So when you have a marshmallow in the syringe and you're covering the top and you pull the plunger, that increase of volume, when it's completely sealed and there's no hole in the syringe, the marshmallow will actually expand to fill that volume. So if there's a hole in the syringe, then the marshmallow obviously won't expand, and this is kind of the same. Our lung will not expand if there's a hole in the cavity. If there's no negative pressure creating a vacuum to pull the air inside of our lungs, then the lungs simply won't inflate. So that's a pneumothorax. Very simple. All right, surfactant. So let's go ahead and define surfactant. This is a lipoprotein complex, and this is produced by type 2 alveolar cells. And what it does is it reduces surface tension inside of the alveoli, and this will prevent collapse during exhalation. So there's a lot of rubbing. The air moving can actually cause them to just crumple up. And so the surfactant is there to help prevent that. Obviously, I'm going to explain how. So Laplace's law is something that we need to know. And Laplace's law is this. Pressure, P, is going to be equal to 2 times our surface tension divided by our radius. So that is Laplace's law. So without surfactant, our high surface tension would make it difficult to inflate our small alveoli. So because of our radius and how small it is, it's easier to do this without surfactant. But there's a lot of surface tension as well on those small alveoli. Gosh. And with the larger ones, it becomes even more increased because there's more radius inside of there. So there's going to be a lot more, or a lot less, pressure. All right, so without surfactant, this is going to increase our surface tension. It's going to increase our surface tension, and that's going to make the pressure just too much pressure. And that's going to cause alveolar collapse, and that's obviously going to affect our gas exchange and our breathing ability in general. All right, let's go back to our question, make sure we're covering everything. Surfactant, blah, blah, blah. CO2 and O2 transportation in the blood. All right, so first, there's 3 main forms of CO2 transport inside of our blood. First, there is our dissolved CO2 inside of plasma. This makes about 10% of CO2 in the body. And it's because CO2 is soluble in our blood plasma, so it'll dissolve into it. Next is our, I have a problem with this word, carbaminohemoglobin. Wow, I said it. Crazy. And this is when CO2 binds to our hemoglobin at a site that's different than where it binds to oxygen on the hemoglobin. So it's just 20% of our body's CO2 is found there in the carbaminohemoglobin. Vocal cords are rough. I have a sore throat from yelling at a rugby game last night, so I'm having trouble speaking. Next, and this is the majority of where our CO2 in the body is found, that is inside of our bicarbonate ions. So CO2 is going to react with water and form carbonic acid, and this will dissociate into bicarbonate and hydrogen ions, and then this is catalyzed by carbonic anhydride. So, our bicarbonate ions makes 70% of our CO2 transport inside of the blood. So, all right, O2 transport in the blood. 1.5% of our oxygen is dissolved in plasma. It's really less soluble in plasma than CO2, so obviously we see a lot less there. And obviously we find the majority of our oxygen in our blood on the hemoglobin because it is bound to it, and 98.5% of our body's oxygen is found on hemoglobin. So each hemoglobin molecule, if it's correctly formed, can bind up to 4 oxygen molecules, and that will form our oxyhemoglobin. So majority, 98.5%. All right, next part, gets a little hairy and I get to draw. So describing our, we're going to do a description of the oxygen hemoglobin dissociation curve and the factors that can influence the affinity of hemoglobin for oxygen, how well it binds oxygen to hemoglobin, and then how do these factors affect our dissociation curve, how easy they pop off. So, to draw a little bit, get my cleaning rag. Because drawing it just makes it better. Oh, sorry. So we have our graph here. And this side is going to be our O2 saturation. And this one is going to be our PO2. The pressure of oxygen. So what's available to the body in pressure. And that's measured in millimeters of mercury, obviously. What we've been doing for so long. I'll put some numbers on here. 20, 40, 60, 80, 100. You can see that. Okay, and then we will also do some percentage of saturation. This will be 40, this will be 60, and this will be 80. Extend up, this will be 100. And again, I am just pulling this from the text, from the class. It's the best way to explain it. So let's go ahead and draw our S-curve. So it'll go like this, and then it'll kind of exponentiate, and then it'll start to level off, obviously, once we get to 100. So that's our basic S-curve, and I'll explain it. Obviously, as there's more pressure of oxygen available to our bodies, it's going to increase our saturation of O2 in the blood, and if there's more O2 in the blood, then hemoglobin will bind more until it gets up here to where it is fully bound. So once it starts getting fully bound, obviously all the hemoglobin molecules are occupied by oxygen until, you get to the top, and then you just can't bind anymore. So factors that will influence our affinity is going to be pH, first off, our Bohr effect. So lower pH will decrease our affinity, and that's going to shift the curve to the right, like this. So once the curve is shifted to the right, if you can see that, yeah, okay. Once it's shifted to the right, that will decrease the affinity because oxygen is being taken up by the acidity of our body, and hemoglobin is not in the right form to accept oxygen. So that'll affect that. The next factor is going to be temperature, and higher temperature is going to decrease our bonding affinity, and that is also going to shift our curve to the right. Let's see. Small p, my bad. See what I have to deal with? Horrible board. So our pH will affect it, our temperature going up will affect it as well. I know how to hold things for camera. As well as higher CO2 levels. Obviously, if there's more CO2 in the body, it's going to displace our oxygen. And yeah, I'll go ahead and write that. Sorry, I'm tired. Ready for a nap. Our CO2 going up will also cause this shift to the right, as well as our 2,3 BPG. BPG stands for biphosphoglycerate in the body, and that's also going to decrease our affinity, causing the shift to the right. I think I got everything. You know, now that I realize it, I think I drew the curve to the left. Yep, I did. Okay. That's a little embarrassing. Okay. No, we'll keep it. We'll keep it. How about that? And I'll explain the inverses as well. Okay, so if there's less CO2 in the body, it's going to shift the curve to the left, which I drew originally. It was on purpose. CO2, less CO2 in the body, we'll shift it to the left, increasing our affinity. pH going up, becoming less acidic, more basic. We'll shift it to the left as well. Better binding affinity. And if temperature goes down, then our binding affinity will also go up. So I think I covered that all. Again, this is going to be our shift to the right. CO2 going up, pH going down, temperature going up. That's going to be our shift to the right. Less binding affinity for oxygen on hemoglobin. And again, 2,3 biphosphoglycerate in the body. More of that will shift it to the right. Less binding affinity. Okay. I think that covers it. So let's talk a little bit about the dissociation curve before I wrap up. A shift to the right, lower oxygen affinity. Oxygen is not binding as well. Oxygen is not going to unload as well from hemoglobin. It's going to stay stuck on there if it was already there. A left shift is higher affinity, and that means oxygen loading and unloading is more effective and more efficient. And I think I covered all of that. Let me double check with the question. I think I did. Question 4, up next.